Greetings folks, it's Professor Fiore, and in this video we're going to take a look at Millman's theorem. What Millman's theorem says is that you can start with a network that consists of a parallel connection of realistic voltage sources, meaning a voltage source with a series internal resistance. You can have any number of these. I'm just drawing 3 of them, but you could have 5, 18, whatever. And you can turn that into a single voltage source with internal resistance. And there's a couple formulas we can use. And I'll just explain how these work. The equivalent resistance over here is the reciprocal of the sum of 1 over Rk. K being essentially which resistor you're talking about. R1, 2, 3, 4, 5, up to some maximum value. So you just do a summation on that. You just have all of these things strung out, so to speak. Meanwhile, the voltage, the equivalent voltage, is equal to this Req you just calculated times the summation of these little fractions, which would be, again, V1, V2, V3, V4, etc., divided by the appropriate R value, R1, R2, R3, R4, and so forth. Sometimes this is written as the summation of Vk times the quantity Req over Rk. In other words, a voltage times a resistance ratio, essentially. All right. Okay, now, first of all, this should not be alarming in any way, because after all, you could always use Thevenin's theorem, right? Thevenin's theorem says you can take a network like this and turn it into a Thevenin equivalent. In other words, Veq would be the Vthev, and Req would be the Rthev. So that's by itself not all that crazy. This is kind of a nice compact way of writing the formula, though, unlike trying to go through with Thevenin's theorem. You know, depending on how you attack Thevenin's theorem, this might be a little bit of work. For example, if you decided to use superposition to find the open circuit output voltage, you know, you'd make a separate circuit equivalent, if you will, for each one of these sources. You'd have 3. You could also use mesh on this, or nodal, your choice. But I'm going to show you a different way, a way of sort of generating these equations. Like, where did these equations actually come from? All right, other than Mr. Millman's brain. Well, the key here, I think, is to just think in terms of current sources, right? Voltage sources don't add up nice when they're in parallel like this. But current sources do, and you could certainly do a source conversion on each one of these. So let's take a look at that. Here's my original circuit. Now, over here I have current source equivalent networks. So for each one of these, each voltage source and internal resistance, I create a current source with its internal resistance, which of course is in parallel. So the resistor value just translates, right? If you've forgotten how to do source conversions, you just bring the resistance over, in this case from series to parallel. So here's 1K, 1K, and then you simply find out what the short circuit or maximizing current would happen to be. In other words, 5 volts over 1K gives me 5 mils. And I would do a similar thing over here, right? For source number 2, I take the 12K, that appears over here, and I would find the maximizing current. 30 volts divided by 12K is going to get me 2.5 milliamps. Finally, over here, translate your R3 over, right? There's the 4K, and then same for the voltage source. The trick here is I flip this source upside down. Notice the plus is on the bottom, so the direction of this current source goes down. You have to pay attention to the directions. It's important. But in any case, we get 1.5 mils for that, right? You take 6 volts divided by 4K, you get 1.5 mils, but it's flowing down. Now, I can take this and do a very quick summation of elements, combination of elements, and come up with an equivalent, right? The currents, we could just use Kirchhoff's current law, are just going to add. I've got 5, 2.5, and 1.5 going the other way, so I would subtract that. And then the resistors, well, the 1K, the 12K, and the 4K are basically all in parallel. So I just put those 3 resistors in parallel, combine up the 3 currents, and I get a single current with a single resistance, which is this. Right? So I take my 5, my 2.5, and subtract the 1.5. We get 6 milliamps for that current source. I put the 1K in parallel with the 12K in parallel with the 4K, and we get 750 ohms. So here is my single current source. And then the last step is to do another source conversion to get back the original voltage source, right? So again, the resistor just transfers over. So 750 in parallel turns into 750 in series. And then we just find out what the maximizing voltage is. In other words, we put 6 mils through 750 ohms and we get 4.5 volts. So this is the equivalent of what we started with. In other words, way back here. Okay? All right, so the theorem basically says I can remove this from my circuit, replace it with this, and the results, in other words, in the remainder of the circuit, the voltages and currents and so forth, powers, whatever, would be identical. There wouldn't be any difference. So let's do that. So here's that set of 3 voltage sources. Here's the equivalent. And I've put in a sort of non-trivial load out here, right? I've got 3 resistors in a series parallel connection, and just to make it more fun, I've thrown in a voltage source, right? After all, it just has to be this series parallel, resistor kind of source. Maybe you have a source, maybe you don't. Could be a current source. I just happen to throw in a voltage source, but whatever. Whatever I get in this circuit should be the same as over here. Obviously, something like this is easier to analyze than something like this. Right? That's the whole reason why you would do it, is you have multiple sources and you can just shrink it down into one, right? So you could kind of think of it as sort of a subset of Thevenin's theorem as far as simplification goes, right? Okay, so let's do that. Without further ado, right, we'll just do a DC analysis over here and see what we come up with. All right, let me put this over here in the center. So could be a voltage, could be a current. So let me go grab, tell you what, we'll grab our equivalent first. Notice this is showing the current flowing down, and we're getting 1.891 milliamps for that, and I'm getting 5.748 volts, right? 1.891 mils. So I come over here. I want to look at R5, should be the same as R8, 3.04K, 3.04K. So let's run that again, right? Actually, I didn't have to run it again, but all right. So there's my 1.891 mils. There's my 5.748 volts, right? The arrow going down. I could have just done this, but just so that you know for sure, I'm not cheating you, right? We did it again, right? So I can check this elsewhere. Let me look at R4. I'm getting a negative about 3.25 volts. Come over here on R7, which is the same. There's my negative 3.25 volts. Okay. Alrighty. So, Millman's theorem is a theorem you never have to use, right? There are ways around it. And to be honest with you, I would never memorize these equations. If you think about it, this equation is nothing more than saying, hey, all these resistors are in parallel, right? It's 1 over the sum of the reciprocals. In other words, the conductance values, right? All right, and what is this? Basically, VK over RK is the current that you got on the conversion. And we're just saying, well, sum up all those currents and then multiply by the resistance. In other words, this encapsulates the source conversions into one equation. But you could just do that manually, right? You don't have to memorize these things. You could just say, okay, I'll do my conversions and I come up with my result. And there we go. All right. More than one way to skin a cat. I don't know why you would need to skin a cat in more than one case. More than one methodology for cat skinning. I don't even understand why you'd want to do that, but it's a saying. Sayings come from weird places. Who knows? But there you go. You got multiple ways of doing it. There's Millman's theorem. Any questions? You know what to do. Put them down in the comments. Talk to you next time. Have a good one.